Hello, welcome to lecture 13. So in the previous lecture, we had discussed the scales of motion. So we said that for various variables that are there in the that are applicable to our motion has a representative scale, and we gave some ideas of the order of magnitude of those scales. So now, based on the scales that we have defined, we will see how the governing equations of fluid flow can be modified. I mean, can be simplified further actually. So we have already simplified the governing the full Navier-Stokes equation into using the Boussinesq approximation, and then we'll see that how a scale analysis helps us in further simplification of these the governing equations for oceanic and atmospheric flows. So now we choose our scales of we choose the motions in a way where the effect of rotation and stratification are important. So this is because geophysical flows are affected by the stratification and rotation, the two most the two very important properties of geophysical flows. So anything where the scales of motion are very different from the scales of motion which are affected by large scale stratification and rotation, those small scale motions are not really affected by the Earth's rotation or the stratification in the atmosphere or the oceans. For example, something which is a flow which is there in a laboratory channel or a pipe is not really strongly affected by the rotation of the Earth. So hence it's important for us for a further analysis and simplification to choose only those motions which are affected by the large scale rotation and the stratification. So we choose the motions so as to satisfy we choose motions to satisfy the criteria of time period greater than 1 over omega. So this means only the flows which have a time scale which is related to, which is near about the frequency of the Earth's rotation and revolution, is the one which is going to be affected by the Earth's rotation and revolution. Of course, I mean, this has to happen. Something which is changing at a much faster scale as compared to Earth's rotation will not be affected by the Earth's rotation. So this is the beginning of the understanding of scales of motion, and we will see how some of these are actually are very important in simplifying our equations. So omega is the frequency here. So t is the time period of motion. So we have also used T previously in, for example, temperature, but of course this is understood that for this particular chapter, for this particular subsection that we are dealing, T is time period. So there might be some overlaps in variables, but I will time and again tell you what those variables mean during those discussions. And omega is the frequency consisting of Earth's rotation about its axis and revolution about the sun. So this omega is consists of both the frequency of Earth's rotation and its revolution about the sun. So the back of the envelope calculation gives us omega to be of approximately omega value to be this rotation rate plus the rate of revolution. So you can make sure that what I'm writing is correct. in the sense that the first part is the rotation that happens in a 24-hour time period. I've converted it to seconds, and then the second part is happens in this in 1 year, and I've converted into seconds. So this is approximately equal to 7.29 into 10 raised to 5 second inverse. So this is the omega. So the choice we have here is that t equal to 1 by greater than equal to 1 over omega, that is the motions the time scales of the motion should be comparable to or larger than the Earth's rotation. So only then this falls under the purview of this subject, that is, it is affected by the rotation of the Earth. So motions, I mean, this is a constraint based on time scale. It's important for us to understand. So this is a constraint based only on time scale. We have not said anything about the other properties of the flow. We have said that only time scale should be constrained by this relationship, inequality. But motions with large spatial scales can also be affected by rotation, even if they slightly deviate from this condition. So motions with large spatial scales can also be affected by the Earth's rotation of Earth, even if they slightly deviate from the time scale constraint. Hence, it is we can say that if we have something which relates the length scales also with regard to length scales of the flow, length scales that could be derived from the rotation rate of the Earth, then we can say that we will have a better constraint, or we'll have a constraint on the spatial scales of the motion. So if let's say U and L are relevant speeds and length scales of motion, so so this is relevant speed and length scale. As we saw in the previous class, U and L are representative scales. So if U and L are relevant lengths, the relevant speed and length scales of the motion, so the trajectory can be affected by the Earth's rotation if time period of rotation is less than equal to time taken by a particle to cover distance L Okay, so time period of rotation is less than equal to time taken by particle to cover distance L at speed U. So as you can see, this not only takes the time as a constraint, this also now brings in distance and the speed as a constraint of the motion. So using this, I mean, just expressing it in mathematical form, so that is, if 2 pi by omega and L by U is less than equal to 1, then the flows then the motion is affected by Earth's rotation. So having said that, this is a constraint which brings into picture both the length scales and the velocity scales of the problem. So in the previous class, we had also seen that we defined the x and the y dimensions with the characteristic length scale L. So we generally in this in our analysis we will not distinguish between both the direction, that is the motion or the speeds or the length scales in one direction, or the time taken for a motion in one direction, that is in the xy plane, will be approximately of the same order of magnitude as it takes in the other direction. However, the vertical direction is special. The vertical direction is something that needs special treatment, and you will see that because of its special properties, the equations itself simplify a lot. So this is what we are trying to achieve now. So it's best to keep the end goal in mind, and then as we proceed in our derivation of the simplified equations. And this also gives us a motivation of why we're doing the scale analysis. Now, so both the horizontal directions are represented by, I'm just writing things down, both horizontal directions represented by the length scale L, the velocity scale U. So we do not explicitly distinguish between both the directions x and y. However, the vertical direction is different. So the vertical direction Z, so the length scales in this direction is h, and in most oceanic and atmospheric flows, h by L is much less than 1. So this is a constraint which will actually keep coming back to us in multiple forms, in multiple places, and this will help us reduce the equations of motion. So h by L is much less than 1, means that the scales of the motion in the vertical direction is much less than the scales of the motion in the horizontal direction. It is either x in the y direction. So take for example a cyclone. A cyclone has a horizontal span of a few hundred kilometers. So however, the vertical length extent of that weather phenomena is approximately somewhere between 8 to 10 kilometers, because it is constrained within the troposphere, and we have discussed earlier what is the height of the troposphere. So this is constrained for approximately 10 kilometers, let's say, and whereas the horizontal length scale is 100 kilometers. So this is an order of magnitude less. The vertical length scale is order of magnitude less. So similarly in ocean, the ocean currents have few hundreds, tens of hundreds of kilometers length scale, whereas the vertical scale is very less. It's a few 100 meters. Let's say a certain current that is flowing on an average will have a few 100 meters of the vertical dimension. Hence, this approximation is valid in most situations where we are dealing with large scale flows in the ocean and atmosphere. We are saying on an average, in general, the vertical length scale is much less than the horizontal length scale. That is the fundamental message of this discussion. Now, based on these, so the scale analysis of the previous lecture and the understanding of the extent of the horizontal direction and the vertical direction, we do a recap of the governing equation, and we see how it helps us in simplifying the equations of motion. Recap of the governing equations So we'll deal with the governing equations for geophysical flows that will include the effect of rotation. So, and we'll of course use the Boussinesq approximation, that is the density variations are only multiplied with the term which has the highest acceleration in the system, that is the gravitational acceleration. The density variations are neglected in other terms of the momentum equation. So recap of the governing equations. This will also, I mean, the reason why we're also doing this is to, of course, first of all, as I mentioned multiple times, is to simplify the equation, try to simplify the equation with some proper justification. Second also is we'll get to the boundary condition, which I had promised earlier, but we have not done yet. So that will hopefully put an end to the discussion around the governing equations, and then we'll move on to the other topics. So first, the continuity equation. So let's start with the continuity equation. So the divergence of the velocity field is equal to 0. So this has the same form. I mean, the divergence going to 0 is same as incompressibility. So this is the same form in the Boussinesq approximation. So now the momentum equation, the total derivative of the u velocity. So first of all, let's write this in total component form. That will make discussions slightly easier. So first is the temporal derivative. The other three terms are the convective derivatives, plus f star w minus f v. So we go back to the momentum equations. Now we have introduced these two terms, as you can see, which are due to the effect of the in the frame of reference being non-inertial. So we had already done during the discussion on the effect of rotation in lecture 6 and 7 that the x momentum will gain two terms, where f star is 2 omega cos phi, where phi is the latitude, and f is 2 omega sine phi, where phi is again the latitude. So w and v are the vertical velocities and the horizontal velocity in the y direction respectively, and this is equal to minus 1 over rho naught del p by del x plus nu del square u. So this is the full equation that has all the nonlinear terms, the rotation term, the pressure gradient, and the viscous dissipation terms. So this is the x momentum. The y momentum equation, let's use a different pen. So this is the x. So the y momentum equation, del v by del t plus u del v del x plus v del v del y w del v del z plus fu equal to minus 1 by rho naught del p del y plus nu del square del square v. So if you're not recalling how the f and f star had come, so please look at the earlier lecture. Sorry, this is f star and this is f. The coordinate frame is rotating, and hence we have the Coriolis term. In the z direction, we have the del w del t plus u del w del x plus v del w del y plus w del w del z minus f star u equal to minus 1 by rho naught del p del y minus rho by rho naught times g plus nu del square w. As you can see, the gravity terms of course appears only in the z momentum equation, because this is the direction of gravity, and the change in density, that is this perturbation density rho, appears only when it is multiplied with the gravity term. There is no other rho term multiplied in any other terms of any of these three equations. That means that rho prime variation is not important unless it is multiplied with the gravitational acceleration. This is the Bose-Risk approximation, and these are the Bose-Risk momentum equation, including the effect of rotation. So now, order of magnitude of the continuity equation. So we have done overview of the scales of motion. Now we are well suited to do the order of magnitude analysis. This will help us reduce the equation, the complexity of the equation. So order of magnitude analysis. So now, starting with the continuity equation, del u del x plus del v del y plus del w del z equal to 0 is the continuity equation. Now we have already defined the scales for the velocities and the spatial coordinates, so we will not repeat those. So this scale says u by L, this dv by dy term scale says so the scale says u by L. I'm just being the first scale analysis, I'm just coloring all of these with different colors. From next time onwards we'll just use the same color, and this is w by h. So these are three terms. So the first term scale says u by L. Why? Because there is a small u appearing and there is a small x appearing, and as we discussed in the previous class, variable u has a scale capital U, variable x has a scale capital L. Similarly, variable v has a scale capital U, variable y has a scale capital L. This also goes back to today's discussion that we are not differentiating between the x and the y directions. That is, both the horizontal directions are assumed to be of the same order of magnitude. Hence, the scaling of dv by dy is also same as du by dx, because there is no difference. We are not distinguishing between them. Whereas the scaling of dw by dz is in terms of the scale velocity w and the scale velocity h for z. So in geophysical flows, the vertical velocity w is generally constrained. So in geophysical flows, which is of our interest, the vertical velocity w is constrained approximately as, I mean, this is as this follows a certain inequality of this kind. So that is, the vertical velocity is less than the horizontal velocity by a factor of this h by L. And because we have h by L much less than 1, this is what we previously saw, this implies w much less than q. That is, the vertical velocity is much less than the components of the horizontal velocity. So in summary, in this, using this argument, I mean, just plain scale analysis, large scale geophysical flows is a statement so large scale geophysical flows are nearly 2D and shallow, h less than, so h much less than L. So height is much less than the length scale in the horizontal directions, and the vertical velocity is much less than the magnitude of velocities in the two directions. So this gives that this is a nearly 2D flow and it's a shallow flow. That is, the vertical variations are not appreciable. Okay, so now in this case, the leading order balance continuity equation is continuity equation is 2D. That is, it just becomes del u del x plus del v del y is equal to 0. So this is the leading order balance. That is, the horizontal convergence in one direction means a horizontal divergence in the other direction. Okay, so if there is something which is coming in one direction, it has to go out from the other direction to maintain the divergence free condition. We can also have all the three terms of the continuity equation of nearly equal magnitude, depending on the ratio of the velocities to their corresponding length scales. In that case, we will preserve all the three terms of the continuity equation. So it might so happen that as we go along, we will, I mean, it will happen that in most cases we'll keep all the three terms of the continuity equation, but in very large scale flows, and also when the ratios are such that the third term can be neglected, that is del w del z can be neglected, the continuity will have only the leading order balance in the continuity equation will only be the first two terms. So this is hence the continuity equation just as a 2D balance. So now once we have done the continuity equation, so the next step is to consider the momentum equation. So we'll start with the momentum equation, and then we'll continue over to the next class also. So the momentum equation, this is again reminding ourselves of our aim is to reduce the complexity of the equation and see if our scale analysis gives us some advantage in that. So the momentum equation has the form, so I'm just writing down in terms of the total derivative. I've already expanded the full momentum equation, so you may go back a slide or two just to see the full momentum equation. Plus f star w minus fv, written it in slightly condensed form for better representation. Okay, so you expand this. I have already expanded the full momentum equation in this slide. So now if we use this whole momentum equation, it's better if we just do it once for the x momentum equation. So for the x momentum equation, let's say we write all the terms and we don't abbreviate or don't condense any of these terms. So del u del t plus u del u del x plus v del u del y plus w del u del z plus f star w minus fv equal to minus 1 by rho naught del p del x plus nu del square u del x squared plus nu del square u squared plus nu del square u del z squared. So x momentum does not have any gravity. So all these terms scale according to their own respective variables. So let's say using a different color, so the first term scales as u by t. There's a time, there is a small velocity here, and there's a time here, so it scales as u by t. The second term scales as u squared by l, because there are two u terms, there is one u here, one u here, and x here. Similarly, the third term scales is u squared by l, because again v and u are taken, they have the same scale variables, so they are not we are not differentiating between the x and the y directions. The fourth term scales as w u by h. The fifth term scales as omega times w the sixth term is omega u, because f is 2 omega sine theta. So the first term on the right hand side scales as p by rho naught L, because there is one p, there is rho naught, there is L. The other three terms scales as nu u by L squared, nu u by L squared, and nu u by h squared. So x and y have scales L, z has a scale h. That is the reason why the scale is the last term scales is nu u by h squared. Here p is a pressure scale we had not introduced earlier, so p is the pressure scale. Now, so we did not introduce in the earlier lecture, but this is the scale which is for pressure. I mean, it can take different magnitudes depending on the type of the flow, but this is similar to how U, L, and W represent the various scaling for different variables. P is a scale for pressure. Now we will see the next class how each of these terms, how we can do a relative order of magnitude analysis of each of these terms, and how some of these terms can be neglected, and some of the most dramatic changes happens with the z momentum equation, and leads to a great simplification of the momentum equations.